Okay, you guys, this is a long one. This is chapter 8, section problem number 39, and this is section 4, and it is about natural and step response for a series RLC circuit. So we have a series RLC circuit. The switch is open before time 0. We have a 25 nanofarad capacitor, and it is in series, or it will be in series once the switch closes, with some resistor of some value, some inductor with some value, and what we know is the Nieper frequency and the resonant radian frequency. They gave that to us, so, no, actually, I stand corrected. We don't know that we're going to calculate that. The Nieper frequency is the alpha, and the resonant radian frequency is the omega naught. And so what we do know are the two characteristic, the values of the two characteristic equations. And S1 is negative 4,000 radians per second. S2 is negative 16,000 radians per second. And the initial energy stored in the capacitor is 9 millijoules. So let me tell you what we're trying to find, and let me tell you how I went about to finding it. And then you should pause the video and give it a shot. So given this stuff, in part A, we want to find the exact values of the resistor and the inductor. And to do that part, what I did was I pulled on the equations for S1 and S2. And once you do that, and you also make use of the fact that we know what the value of the capacitor is, you will come down to two equations and two unknowns, and two equations and two unknowns can be solved. And from that, you should be able to find the alpha, the omega. That will become important in the next part, because we need to find, well, down the line, because we need to find general equations, and to do that, we need to know the response of the circuit. So doing that, you will be able to find R and L. And then in part B, we are looking for the numerical values of the inductor, or I0. This is the current. It's current through the inductor and the resistor, since they're series connected. So we're looking for that current right at time 0. And we're also looking for the change in the current at time 0. And to solve that, we are going to pull on the properties of the inductor. How does it behave when switching happens? How does voltage and current change in an inductor? So that is what I did to solve part B. Part C, we want to find the general equation for the current. And to do that, first you need to take a look at alpha and omega that you found in part A. And once you know that, you should know whether the response is critically damped, overdamped, or underdamped. That will drive your set of equations. So once you know that, you know which equations to use. There's a nice summary at the end of the chapter. You can go to your set of equations and find the three that you need. And then from there, you need to know some properties about inductors in order to set up the three equations. And once you set them up, then you have enough variables and enough unknowns and enough equations to solve. And that's how I did part B. Part C. Part D asks, how many microseconds after the switch closes does the current reach its maximum value? The key word here is maximum. And the key to solving this one is to realize that the inductor current, the equation for the inductor current is a decaying exponential. So it's concave downward, and that means that we can use calculus to solve this. So the derivative, a derivative of a function will give you either, will tell you whether you have a maximum or a minimum or a point of inflection. In circuits, we will always have a decaying response. Therefore, it's always going to give us a maximum. So So we can use that property of calculus to differentiate set to 0, and that will give us the time, exact time, when we will have a maximum current. And once you find the maximum current, you simply plug it back into the formula in order to solve for the exact value of the current. So part E asks the maximum value of the current itself. Well, there you're going to go back to part D and plug in the time and get out whatever amps, however many amps you get out. That's how I solved that one. Part F, to find the general equation for the voltage across the inductor, go back to chapter 7 and look at your relationships or your equations for the inductor. There is an equation there for voltage across an inductor. I believe it's L di dt. So you know L, by part E, you know di dt, put them together, and that is the answer. Now pause the video and try it. You won't learn by watching the solution before trying it. I gave you a guideline of how I solved it, so give it a shot. Alright, so now that you have tried it, let us go ahead and solve this equation. So to find R and L, I just said, well, we know that S12 is equal to negative alpha plus or minus the square root of alpha squared minus omega naught squared. So that means knowing S1 and S2, we can construct two equations and we have two unknowns, so that's a very solvable. We can find alpha and omega naught. Let's go ahead and do that. S1 is going to be, well, let's just plug in the values. S1 is negative 4,000. So negative 4,000 is equal to negative alpha plus the square root of alpha squared minus omega naught squared. S2 is negative 16,000. And that's equal to negative alpha minus omega naught squared. Alpha squared minus omega naught squared. So you might be wondering, how did I know that negative 16,000 was S2 and went with a minus sign, and how did I know? Because they didn't tell us or specify that. Well, the characteristic equation is always going to be negative alpha plus or minus. So if this number is negative, then that means S2 must be getting more negative. So it has to be the greater negative number. So now, but in any event, if you didn't know, the math would probably yield it anyways. Now we can add these two equations together. And the reason I want to do that is because I really want to get rid of the radical there, because radicals make math very messy. So what we can do is we get negative 20,000 here is going to equal negative 2 alpha. That tells us alpha is 10,000 radians per second. So that's k rad per second. And we're going to put this value up here because we need it for later. 10,000 k rad per second. So now that I know what alpha is, I can just plug it into either one of my original formulas to find omega naught. So I know that's 10, that's 10k, 10k, 10k squared. I'm not going to solve this. Well, yeah, I guess I'll solve it. So minus 10k, minus 10k, that will give me, okay, so this will give me, I made a mistake somewhere. Let's go back to alpha and omega naught, because 10k. Oh, I have a sign error in setting that up. So let's set it up again. So I have negative 4,000, 4k, negative 4k, and that's equal to, I found out that that's 10k, so I'll have a negative 10k plus the square root of 10k squared minus omega naught squared. So we have 10K to both sides. So this will give me 6K is equal to the square root of 10K squared minus omega naught squared. Square both sides. And this will give you 6K squared is equal to 10K squared minus omega naught squared. Running out of room. Subtract 10K from both sides, 10K squared, and take the square root. So this will give me negative, well, this will give me negative 64 million. 64e to the 6 is equal to negative omega naught squared. Solve for omega naught, and you should come up with an answer of omega naught is equal to 8,000. So 8K rad per second. So now we're getting closer. Now we're going to use the very definition of alpha and omega to find what we need. Alpha is equal to R over 2L. Omega naught is equal to 1 over root LC. We can't start with this one because we don't know two things. We don't know L and we don't know R. And right now we do know alpha, and we know that's 10K. And we know omega naught, and that is 8K. So we have to start with this one because we know C. So this is L times 31.25 E minus 9. So swap the places for L. Well, you can't exactly perfectly do that, but you can square both sides. Get rid of it. So we have 8K squared is equal to 1 over 31.25 E minus 9 times L. Now we can swap the places of L and 8K squared. L goes here. And in the denominator we have 8K squared. So I would like to double check to make sure I didn't make any dumb, stupid mistakes. And we're good. So when you solve for that, you should come up with L is equal to 1/2. So now we know that this is equal to 0.5 henries. So if this is 0.5 henries, so this is times 0.5, then R is going to be 10K times 2 times 0.5, and that is going to be 10K. That is part A. For part B, we are looking for two things, and they're quite different. The first thing we're looking for is the current across the inductor and the resistor. They're the same current because they're series connected right after the switching happens. The other thing that we're looking for is the change in the current across the inductor at time 0. So we know right before the switch opens, there's no current through the inductor. It has no energy stored in it. It's not connected to any power source. So we pull on the property of the inductor, and that property is that an inductor cannot change voltage, an inductor cannot change current immediately before and after switching. It just takes time for the magnetic field to build and change. It will definitely change voltage like crazy to try to maintain 0 current, but it can't change current, so we know this has to be 0. 0 amps. It'll change current. Changing voltage means changing current, so it's going to change current. Now, how will it do that, and how will we find that? We are going to find that using, well, first of all, we don't have nearly enough information. Ultimately, we are going to use this property for the of the capacitor. There's a relationship that says V voltage across the capacitor is and we kind of is L times di dt. And by using that, we can say, well, di dt right after the switching happens is going to be the voltage right after the switching happens, and that is divided by L. So we can say that. Except for, we don't quite know what the voltage is across the capacitor. We have to find it indirectly. We do know what the energy is in the capacitor. So remember a couple of things. So we know the energy that's in that capacitor. We don't know the voltage. We also know there's a property about the voltage, about capacitors, and that is capacitors cannot change voltage immediately after switching occurs. So we know whatever energy voltage that we find at time 0, it will also, before time 0, we'll find that indirectly from that 9 millijoules, that will remain the same after the switching happens. So by finding the voltage before the switching, we also know that the voltage after the switching. And that's really what we're looking for, because that will tell us the change in the current in the inductor. So let us go ahead and pull up the relationship between capacitors and energy. So we know the energy stored, the initial energy stored in the capacitor is 9 millijoules. And we also have this relationship, energy in the capacitor is going to be 1/2 CV squared. So we know that, we know energy, we know capacitance, therefore we should be able to find the voltage, the general voltage across the capacitor. So this is 9 millijoules, that's going to be 1/2, and this is going to be times 31.25 E minus 9, voltage squared. And you can go ahead and solve for voltage, because that's simply the square root of everything. Once you multiply by 2 divided by 31.25 E minus 9, your voltage should be 24 volts. So now we know that this is 24 volts. That's right, the initial voltage of the initial voltage drop across the capacitor. And we know that inductance is 2.2 henries or 0.5 henries. So that tells me that the initial change, the di dt, the initial change right after the switching happens is 48 amps per second. All right, and that is the answer to part B. Part C is finding the general equation for the inductor current. And to do that, we have to know there are three ways that a circuit can respond. It can respond, it can be critically damped, it can be overdamped, or it can be underdamped. And depending on the type of damping you have going on, you're going to use different sets of equations. So in this case, we know alpha is greater than omega naught, which means we have an overdamped circuit. Recall that when omega naught is greater than alpha, we have an underdamped response. When they're equal, we have a critically damped response. So knowing that they're overdamped means we will use these sets of equations. These are their general equations for the different responses. So I am going to erase some information here. And so the three equations that we need are I of t is equal to I final plus A1 prime e to the S1t plus A2 prime e to the S2t. And I of 0 is equal to I final plus A1 prime plus A2 prime, and di dt of 0 is A1 prime S1 plus A2 prime S2. Those are the three equations that we need to solve to find the general equation. So let's look at the general equation itself. It's saying that it's equal to the final current times A1 prime plus e to the S1 plus A2 prime times e to the S2t. Notice that once the switch closes, we are not connected to any independent power sources, so everything is going to dissipate, and ultimately at time equals infinity, the voltage, the current across the inductor will go to 0, the voltage across the capacitor will also go to 0. So that I final is 0. Great. So now we know S1, we know S2, all that remains is to find A1 and A2, and luckily we have two equations to do that with. So let's tackle this equation. The current at time 0 is equal to A1 prime plus A2 prime. Well, the current at time 0, remember, we have an open switch, and because inductors cannot change current instantaneously, that current has to be 0. So that means my first equation is 0 is equal to A1 prime plus A2 prime. That means that A1 prime is equal to negative A2 prime. And that's very good. So we have over here, we have A1 prime is equal to negative A2 prime. Now we can substitute that into the third equation, which says the rate of change of the current at time 0 is equal to, and that's of course di dt of 0, is equal to A1 prime S1 times A2 prime S2. We know S1, we know S2, di0 dt we solved in part B, so if we can substitute A1 is equal to negative A2, then we have one equation, one unknown, and we can find what A2 is. Let's do that. di dt of time 0, we found in part B. We said the rate of the change of the current through the inductor is 48 amps per second after the switching happens. So we said that was 48, and that's equal to A1 is equal to negative A2. So we'll substitute that in right now, call that negative A2 prime. S1 is, I erased it, so I have to pull on my sheet. So S1 is negative 4,000. I think S1 is negative 4,000. Hang on. S1 is negative 4,000 plus A2 times negative 16, negative 16,000. Okay. So now we have one equation, one unknown. This becomes positive 4,000 A2. Positive 4,000 A2 minus minus 16,000 A2 is going to give you negative 12,000 A2. So we got negative 12,000 A2 divided by, it's over 48. So A2 should be, I'll double check because, well, 48 into 12 is 4. So that should be negative 4 milliamps. And since A1 is just negative A2, A1 must be positive 4 milliamps. So now we have everything that we need in order to make a general equation. So let's just write it out. The answer for part C then is the general equation for current through the inductor is IT is equal to A1, which is 4 milliamps, e to the negative S1, negative 4,000, T minus 4, e to the negative 16,000, T, and that is it. That milliamps. So that is your answer for part C. For part D, they want to ask you what time is this current at a maximum? And also what is the value of that current, the actual current? So in order to solve that, we're going to take the derivative, and we don't have to question whether the derivative, and we're going to set the derivative to 0. We don't have to question whether that represents a max or a minimum. or point of inflection, nature dictates that. So the behavior of a first order RL circuit, a series connected RLC circuit, is always going to be a decaying response, which means it will always represent a maximum. So it will always be concave down. So let's take the derivative of that. So di dt, that's going to be negative 4,000 times 4, so negative 16,000 e to the minus 4,000 t. This is negative 16,000 times negative 4 will give me positive 64. E to the minus 16,000 t. Set that to 0 because that's going to be a point of maximum. Okay. So when we solve that, let's move this 16,000 over here. So if I move that to the other side of the equation, it becomes positive. And this becomes equals. Now, I need to get e's on one side and numbers on the other side. So I'm going to divide, to get rid of this coefficient, I'm going to divide by 64,000. And then to get this e on the other side, I'm going to divide that by e to the minus 4,000 t. So on this side, I'm going to have 16 over 64. So I'm going to replace that with 16 over 64. Exponents subtract, so negative 16 minus negative 4,000 is going to give me e to the negative 12,000 on this side. E to the negative 12,000 t. So now we need to bring the t down and solve for the t. That means we take the natural log of both sides of the equation. So that will bring the t down and give me negative 12,000. So this brings the exponent down, and this gives me negative 12,000 t. Divide both sides by negative 12,000, and that will give you t. When you put that into your calculator, you will find that the time where you have maximum current is 116 microseconds. So that is the answer for part D, as far as the time piece of the question. 116 microseconds. The actual maximum itself is, if you go back in the video, you found where I said had well, we don't even need to go back in the video. This is easy to solve. So di dt, or the maximum, so at this time, so all you have to do is plug in 116 microseconds. So here, put in 116 microseconds. At this t, put in 116 microseconds. When you do that, the maximum current will come out to be 1.89 amps. So that's the maximum the current will be. That is part D and part E. So for part F, we want to find the voltage across the inductor. So in order to do that, we need to find the formula for voltage across the inductor, and that formula is VL of T is equal to L di dt. Now notice the di dt is not the one that we found in part B. Why not? Because that di dt is for that instant in time, and we're looking for a general equation that will actually describe that instant in time and all other instances in time. So we're looking for a general equation. We know that L is 1/2. Now we need to find di dt, and we found that actually in part D and E when we were looking for the maximum current. And we needed to do that because a derivative gives you a max, min, or point of inflection. So, di dt, well, I'm just going to, you can go back in the video, but it's negative 16. It's also very easy to solve, and it's an easy derivative. E to the minus 4,000 t plus 64,000 e to the minus 16,000 t. So that means the general equation is negative 8,000 e to the minus 4,000 t plus 64,000 e to the minus 16,000 millivolts. Or, more neatly, it's going to be negative 8 e to the 4,000 t plus 64 e to the negative 16,000 t volts. And that is all the answers to all the sections of problem 39, section 8. If you got help, please share the video or like the Facebook. Thanks.